Hey, hello everyone. My name is Seongjae, as the session chair introduced, and today I'm going to talk about going with semiconductor memory device technologies for future electronics, as mentioned, as introduced. So I'd like to start with my research background first, and it can be laying out some my research expertise and experiences to the audience today, and there will be a small part of my short self-introduction to myself. So the semiconductor device technologies, semiconductor technologies more widely has been driven by Troika. You can see the backside picture, Troika driven by a Roman soldier, and the three horses driving the Troika for semiconductor technology are materials, processing, and device circuits, as you might be already well know. So I could see some big changes in technological directions in the most recent ITRs. ITR stands for International Technology Roadmap for Semiconductors, and we can see the ITRs issue and more, because at some point, maybe 2018 or 17, it was converted to IDRS, as I can show on the next slide. But in the latter part of the history of ITRS, a big change was observed, which was the merge of low operating power and low stabilized power technology tracks. The LOP and STP and HP. HP stands for high performance, and these three tracks are the mainstreams of in which the semiconductor technologies should be developed for. So the two tracks, LP and STP, were merged into low power. And another big change that can be found in HP track is even though they did not abandon the high current drivability requirement, the driving voltage was permanently reduced down to the LP value, 0.86 at voltage. You can see in the table. So the implications we can draw from this picture is the key for the future electronics lies in low power rather than the high performance. Of course, the demands on high performance systems, high performance integrated circuits will not be decreasing. They are always around us, and we always need them. But its velocity of demand on the mobile electronic appliances will be found, as you already do. So the LP requirement, it has the key for the future electronics. I can say that. So as previously mentioned, the ITRS has been changed to International Roadmap for Devices and Systems. So in the previous roadmap of ITRS, all the categories that can be found in the semiconductor engineering about RF design and interconnection design and software manner design, etc., and device and system parts were only occupying only part of that. So we are living in the era in which devices and systems are more important and need to be emphasized. So, we need to put our eyes on some rows in the table. First one is logic device structure, and colored in blue, and the material in the green box, and transport scheme in the red box. So for the material, because the material is the starting point of semiconductor devices and higher level system architectures. So if I start with materials, we are living in the silicon era. We are living in the silicon wares era. So the group 4 material should be emphasized for silicon compatibility. Silicon compatibility is warranted by mostly by group 4 materials. Silicon germanium and strained silicon or strained germanium are also is more or less the same with the silicon germanium. So the straining engineering means the enhancement of carriers can be either electron or hole, depending on the stress is made in the tensile or compressive manner. So 3,5 compound semiconductor or purely germanium can be introduced, but locally to the silicon substrate until the end of electrons. Maybe we cannot abandon silicon platform, silicon substrate, because the overall fabrication cost can be greatly reduced down to a manageable range if the silicon platform is prepared. The other functional materials can be introduced locally into the active area onto silicon platform, but we cannot leave silicon substrate. So most of the materials are physically or chemically silicon compatible or mechanically by bonding, for example, by mechanically it can be silicon compatible. So later, so we can be more interested in transport mechanism, transport scheme. So as you know, the scaling history of device can be understood as the history of semiconductor engineering. So if the scaling limit is really met at some time in the near future, we have another choice for driving the silicon devices further by changing the transport mechanisms. It can be a ballistic transport tunneling or junction FET. Junction FET means that there is no electrical barrier between source and drain. Source and drain, I mean the source and channel and drain, because all the channels are doped in a single type of dopants. So negative capacitance MOSFET and spin tronics can be introduced to drive the future electron devices. So the structures, so all the once all the materials and mechanisms are prepared, we can think about very novel structures that can counter the electrostatic effects in the devices for better performances. So we are living in a silicon verify era, and we are also you can see that we are also living in a film FET era, and that's why fully depleted and partially depleted. That's why we're emerging in the past, and we are facing to the GAA era. Right after film FET technological node, we will be living in the GAA and monolithic 3D. But GAA means gate-all-around structure, which can be termed into another name of non-wire. And monolithic 3D is litho, or lithic means stone. So monolithic is one stone, and that stone will be silicon, as I emphasized shortly. And so everything can be realized with different functionality layers on the same silicon platform, same silicon wafer by bonding, or at this moment, the bonding is the most advanced technology to link up different layers. But the best thing we can expect is fabricate all the different circuits vertically by batch production. I mean batch processing. Okay. So I would like to lay out some of my research experiences. The first thing I emphasize, the material is the starting point of all the semiconductor-related engineering, especially to device. So ab initio calculation for silicon compatible group for material design. The ab initio calculation, ab initio means from the beginning, from the first principle in Gachon, and ab initio calculation is a very famous, very prevalent method used in the material sciences or engineering. But I just adopted that calculation method to predict the material properties of unknown alloys. But I'm particularly focused on silicon compatible group 4 materials. Group 4 include carbon, silicon, and germanium and tin on the same column, and they are believed to have silicon compatible because they have the 4 outermost electrons. So if you will perform the ab initio calculation of certain material, you can minimize the volume. In other words, you can minimize the system energy, total energy, and determine the atomic distance between adjacent atoms. And based on the structural optimization, we can extract the materials, very well-known materials like electron affinity, electron and hole mobility, energy band gap, things like that. But one drawback that can be found in average calculation is always the calculation is always based on 0 Kelvin simulation. Okay, so that is a little bit that can provide us with a little bit different results, physical properties of results compared with those in 300 Kelvin we are living in. So the below graphs demonstrate the EK diagrams. Some of you might be familiar with these graphs, or might not be. But silicon, germanium, and germanium-tin EK diagrams can be drawn from this ab initio calculation. So the synthesis of unknown material usually takes much time and cost. So like just the other implementation of electronic system or devices. So we have to perform the atom level simulation at the first point, and we can draw this EK diagram or electronic structure. And if you map these figures into the position or the space domain, we can call it an energy band diagram. So very interesting and picture, and we can draw a lot of information from these figures. And then we have to go through some empirical experiments. So low temperature processing of germanium and germanium-tin was tried before, and material characterizations were performed. So low temperature is a kind of fascinating term in the semiconductor engineering, because low temperature is shorter time, and shorter time means shorter time to market, and that is that gives a company a competitiveness. But one drawback that can be found in the low temperature processing is the material property that we cannot. It is very difficult for us to expect a good crystallinity of material from the low temperature grown materials. So the material properties, general properties, is quite different from what we know from the real crystalline structure. But there's a good advantages feature for, as I mentioned, in the perspective of cost effectiveness and time effectiveness, we can pursue some part for low temperature processing. So TEM and SRLB and other characterizations methods can be applied to identify the material properties in mechanical and electrical and sometimes optical characterizations. So strained silicon and copper interconnect and high copper material in combination with the metal gate have been found in Intel. So the motivation of germanium-tin technology can be found in the strained silicon. So by introducing germanium into silicon, we can expect a better, higher hole mobility. And if there's a tensor strain imposed on silicon by the incorporated germanium, we can also expect enhanced electromobilities. So what germanium did in silicon can be expected from tin. Germanium has higher electromobility than silicon and much higher hole mobility than silicon. When it comes to hole mobility, germanium has the invincibly high hole mobility compared with other well-known materials, including group 4 and silicon and silicon carbide and other 3,5 compound materials. So what we can expect from germanium when it is incorporated into silicon can be again expected for tin in germanium. So if you incorporate tin atoms with a small portion into germanium, you can further increase the electron and hole mobilities. Okay, so later, more recently, polysilicon, particularly strong silicon processing material characterization are solving these days in my research history. So the above figures demonstrated cross-sectional and cross-sectional TM images, implant and cross-sectional TM images of different polysilicon thin film, and the electrical, optical characterizations were performed. So by performing the XLE, we are allowed to know the effective size of crystal light. This is too small. This crystal light is too small for us to tell it is grain, much smaller than grain. So the crystal light, the size is 10 to 20 nanometers. In the past, polysilicon electronics were prevalent in particularly in display TFT technologies, but in these days, the polycrystalline silicon is gaining more increasing demand and interest for the three-dimensional VLSI having different layers with different functions. So beside the crystalline silicon substrate, the other channel materials can be silicon. If we insist on using silicon, we should take polysilicon because there's no way of expect crystalline silicon on interlayer dielectric or intermatter dielectrics. So deposition and some post-deposition annealing will be the best solution to get some crystallinity to some degree. So, but the polysilicon researches in the past is different from what I am pursuing these days because the biostructure is scaled down to below 100 nanometers, and the grain, some grain reaching a few or some tens of micrometers have been shrunken to 10 to 20 nanometers. So in these circumstances, the material properties become totally different, although we can call them commonly polysilicon. So mobility or electrical and other optical characteristics should be found again, assuming that we are dealing with a totally new material. So inventions of novel structres based on these material studies, we can, after all, we can go with the device simulation, device design and fabrication. So I have been focused on polysilicon and silicon germanium, as I briefly mentioned in the previous slides. So heterostructure and FinFET structure, those are not arbitrary. So I can say that those devices are surely on the upcoming technological node. So the nanowire, heterostructure nanowire, and heterostructure FinFET, and the inverted T-shaped FinFET and polysilicon FinFET, things like that, all of them can be welcomed by the integrated device manufacturers like Samsung or SK Hynix and the international companies. So if we perform the TCAS simulation, we can expect some non-ideal effects induced by quantum mechanical effects, not just not the ones that can be determined by a simple drift and diffusion relations. So there are many unknown, unpredictable phenomena that can be induced by the quantum mechanics. So we should be relying on high precision TCAS simulation. So the below the raw figures demonstrate the TCAS simulation results. The silicon compatible materials, silicon, germanium, and germanium-10 have been considered for the actual materials. So device fabrication silicon germanium. This demonstrates one example of one of the most recent research results of mine. So the heterostructure the helper structure is constructed in the radial direction: silicon core, silicon buffer, and silicon shell, silicon germanium shell, and high copper material as the gate electric. And the metal gate was formed to fabricate non-wire horizontal non-wire FET. So it showed a successful IV characteristics, as we can show in the left lower figure. So because this is the PMOS, the current shows an increase in the left outward direction. So the center shows the microscopic view of the fabricated devices, and the other shows the TEM, transmission electron microscopy, or cell images while doing the fabrication. So memory. So today, previously I showed some research histories. There are many other devices I have designed and fabricated, but for a limited time, I showed just the trajectory we need to follow in order to implement or realize our ideas into real hardware in terms of device. So I would like to turn the story to memory, which is the main topic of today. So memory is, we are very familiar with memory. Okay, memory is also one of the most favorite songs in the world, loved by Koreans. So that is one scene from musical Cats. So there's a song, memory, right? And memory is a certain word that reminds us of our mental biology for limiting our brain capabilities, which makes us nonsense. This can be more clarified in the very next line. Memory is always something that calls for our willing to do better about it. We want better memory capabilities, right? And through electronics, as electronic engineers, for us, the first integrated circuits by by Fairchild and Intel were also memory. So this historical fact reflects that how much we like memory, how much we want memory, how much we want to improve memory capability depending on some other pressures by our hands, right? We have in the world best in memory technology. We have sustained a world best positions for maybe 30 years since 1992, as I remember. But memory is not just a technology term that can be found in the semiconductor engineering or company, but something more than that. So people like to say the Korean people are people of Zhong, people of Han. I don't know how terminology can be translated into English, but you might be very aware of their feeling, right? So if you search some songs and some artworks from Melon, I did it myself, and I could find memory from artist name and song name and album title, and the number reached 18,600 or so, and the memory songs. The songs including memory and lyrics reached almost 10,000, a little bit less than that. Okay, so 9,500 or so. So this fact is also reflecting the fact that a human and we are really eager to having memory and not to lose memory. Okay. So I used to ask my students in the classroom or outside education opportunities to and ask the students and audience which capabilities between calculation and memory do you prefer? So in that case, 80% or 90% of students said memory surely. Okay, so the same thing can be heard from the audience today, maybe, if I ask. So most of the people like to have better memory capability than arithmetic calculation capability. So So the Intel and Fairchild first productions were memory, the 64-bit mouse SRAM, first fabricated by Fairchild in 1964, and first commercialized by Intel in the similar year. 1964 is 64 bipolar SRAM, and that technology was based on bipolar transistors, and the model name was 3101, and Intel 1101 mouse SRAM. This is the historical product. The first polysilicon gate technology was adopted, and the first invention was announced in 1969, and mass production. The concept of first mass production of semiconductor IC shell was developed in 1101 in 1971. So research is on industrial semiconductor memory devices. So requirements for industrial memory technologies. So I can summarize. There can be many requirements to be for some memory devices, memory technologies to be the ones that really preferred and that are really preferred by the company mass production companies. But I can summarize 3 out of them. The first is silicon processing compatibility. This is strongly correlated with mass production, and can be welcomed by the existing fabrication lines. And large thermal budget. Large thermal budget is long time and high temperature, and so large thermal budget processing is one good advantages. The requirement that is needed for to be industrial memory. And this device has the robustness and reliability. So thinking with the common sense, the high pressure and high temperature are the ingredients to get the good quality materials, right? So based on the good quality materials, strong material, we can fabricate better devices, of course, and high device scalability, integration density, and with low power operation capability. As I emphasized in the previous slides, the low power LP is the key technology we need to follow in the future electronics. No matter it can be large devices or memory devices, low power is the #1 priority in making electronic appliances. So for the industrial memories, I once researched on holding-down charge trap flash memory. I would like to show the device fabrication shortly first. Actually, this was the topic of my PhD thesis, which was earned in 2010, 11 years ago. So the right upper figure shows the device schematic and the circuit symbols of the array. And more specifically, the charge trap NAND flash memory is based on bandgap engineering. So not like the material compositions, panels, nanos, or some other material step. I introduced ONO, 5 layers between the counter gate, because the insertion nitrile layer between the tunneling and the intermediate oxide layers has an effect of boosting the program and erase speeds. As you can see from the measurement results, the gradient, the diffusion gradient in erase operation shows a higher gradient when the bandgap engineered storage node is applied to the flash memory. And sidewall-space patterning is demonstrated step by step, and the device fabrication and the 2x4, 4x2 array is demonstrated by the microscopic view. So all these fabrications were performed at Seoul National University at ISRC. So I would like to thank all the professors and other co-workers who founded and managed financially and technologically the very wonderful institute at this moment again. So I used safety masks and I still have the run sheet for fabricating devices, the fold and land, and enrich it 126 steps, except the test runs. So it was quite a long time, and took quite a long time, and I used the large number of maths, which was quite complicated. But I firmly can say that most of the semiconductor technology and physics were obtained at Seoul National University. Okay, so CTF memory measurements and photo work. So the two identical flash memory cells are facing to each other with an intervening silicon film. And the silicon film thickness was split into 80 nanometers and 60 nanometers and 20 nanometers. So the goal is to make the identical cells operate independently, not giving interferences to each other. So you can see the identical and independent transfer curves that can be drawn from two identical cells, and the film width was reaching down to 10 nanometers actually, but unfortunately the device was broken down permanently right after performing the programming erase just one time. But I just wanted to leave that figure for keeping. Okay? And the threshold voltage shift, that graph shows the paired cell interference between given each other. And there's two ways of, it was found that there were two ways of minimizing the paired cell interference. The one thing is the processing approach. We can increase the doping concentration of channel and the fin-shaped channel, and electrical method can be also skimmed. So the right counter gate biasing has an effect of reducing the paired cell interference. The paired cell interference was a kind of specifically named term, but it can be found in everywhere in this era of extremely highly scaled NAND flash memory array. And I once researched on PRAM materials, and so there were some reports on the effect of silicon dioxide doping into GSP PRAM. So the better characteristics were found from the researchers, but would like to study further in the mechanical and physical characteristics of the silicon dioxide doped GSP PRAM. So the results shows the phase transition temperature is increased as a function of silicon dioxide doping concentration increase, and the the finer stresses are merged or converged regardless of the starting doping concentration, but the initial stresses are significantly different. So the main results of this work was the dark side, maybe the side effect of silicon dioxide doping, but I believe this research can compensate, can make some little bit perfection in PRAM researches for industrial production. So our research scale random access memory and hafnium oxide has been well known as the switching material. More recently, it can be also adapted to ferroelectric field transistor, but it was used as the gate material if the thickness is reduced down under a certain limit, and it can be also utilized as switch material. And this is the one of the early researches on hafnium dioxide-based resistive switching RAM. Also, I wanted to have an eye for the effect of zirconium dioxide doping into hafnium dioxide. So, in short, the parameter, operation parameters as like with a current or resistance with the voltages, that voltages are more sharply distributed by zero current doping. And these two are researched by co-workers in Stanford University and some researchers in niche professors. And and when I come back to Korea, I also have contributed, dedicated much time and effort to study and to research the resistive switch wireless memory. So one thing is silicon nitride around, which was cooperated with Seoul National University for a long time, and we have derived very numerous meaningful results. And in session with that, once I studied about germanium oxide RM, silicon nitride and germanium oxide are both silicon compatible. So there are many switch layer materials. If you look into previous recently published papers, there can be really many materials, but the most of the researchers are not really interested in silicon compatibility. So one thing I would like to emphasize is the silicon compatibility to make the IDM manufacturers to be interested in our research results, and that can also contribute the semiconductor industry of our country, Korea. So germanium oxide RM demonstrated this at the center, that IV characteristics, and I further went into the device modeling. The circuit model of development of circuit model of certain devices, logic devices or memory devices with unknown IV characteristics, IV relations need to be found for higher level simulations or system design. So the last thing, always the last thing I usually do after device material characteristics and device fabrication and measurement is the device modeling for circuit simulation. So the goal is provide some circuit designers with H-spice models that I have developed. So array modeling, and the device should be fabricated in the form of array, as you know. So this simulation, circuit level simulation, can be performed for identifying the array level characteristics. So H-spice is the most frequently used circuit simulator, and there are others too. And recently, I came back to flash memories again. The flash in an extremely harsh environment. So I applied the gate stack, charge trap layers, which is called malnus. That is actually currently used in the industry for flash memory manufacturing. So I fabricated that device, and with an intent, high energy particles were irradiated into the fabricated devices. So the high energy particles were ions, argon ions, and electrons that can be easily found in the ion implanter in the fabrication facility, and the high energy electrons can be found in the SEM microscope. So after injection of high energy particles for a certain amount of time at a certain amount of energy, what can be commonly observed is the reduction of the maximum capacitance, and the memory window is reduced too. So the final result can be could be derived as the gate. Gate was permanently broken down. The gate atomic matrix is severely broken, and the high parasitic resistance is introduced in series with the capacitor of the flash memory, and that reduces the capacitance, effective capacitance. So the reduction in capacitance means the difficulty in identifying on and off state of the flash memory device because the capacitance, torque capacitance is linearly related with the drivability at an operation voltage, read voltage. And the memory window shrinkage is also a critical issue when it comes to memory operation. And flash memory, we visited floating gate flash. So before it was about 2009 or 2010, so as far as I remember, when this charge-trap flash was has the predominance in flash memory. It's before that time, floating gate flash was predominant. So floating gate means the gate is fabricated by prepared by polysilicon layer. So in most of the literature, the thickness of polysilicon floating gate was 40 nanometers, more than 30 nanometers, 40 nanometers, 50 nanometers or so. But I was questioning how thin it can be driven, it can be deposited. So I tried with 10 nanometers, and although the memory window was a little bit shrunken compared with those that can be found in the past literatures, at least we can expect more than twofold. Actually, 2.5 memory window can be expected from that highly scaled floating gate thickness. That is comparable to a nitride layer thickness in the CTF memory. So in some applications, the floating gate flash memory can be also recalled again because it also has the silicon compatibility and can be also applied to embedded flash memory technology in the processor. So recently, I have been working on capacitor-less dynamic random access memory, or shortly it can be termed as one-to DRAM, one transistor DRAM. So the conventional, if you reflect the fact that the conventional DRAM has a structure of one transistor and one capacitor, one-to DRAM sounds good, right? So because of the resistance capacitor, we can the speed and the absolute value of memory storage is lower, smaller than the NAND flash memory. Okay, so one thing we really need to do is remove the capacitor from DRAM. But the biggest drawback of one-to DRAM is relatively small, relatively shorter attention time compared with the 1-to-1C conventional DRAM. So the tail, Six Sigma tail tells that the tail is located at 64 milliseconds for the conventional DRAM DRAM, but in which the retention is mostly determined by the diffusion, very fastly diffusion carriers programmed into the channel, floating channel. So there should be some ways. I should have prepared some different methods other than storing the carriers within the electrical barriers. So one thing is to introduce polysilicon. Polysilicon is used for everywhere, right? So polysilicon can be introduced as a channel material also into the one-to DRAM, and it has a boundary or crystal life structures, very minute structures under the gate in the channel. So it has an effect of trapping the carriers for a very short time, but relatively longer time than compared with the diffusion time of naturally disappearing carriers by diffusion. So, the experimental results shows that a few seconds, more than 1 second, reaching up to 6.8 seconds were achieved for retention time. This was published in the Boston Letters 2 years ago. And the other one-to DRAM technologies have been cultivated, developed so far. So two-terminal thyristor and polymer structure and polysilicon down there, and physical the one-to DRAM where the physical barriers like physically deform the silicon, what can I say, bucket or some yes, back structure, or that can be also made by oxide, thin oxide layers. So we can introduce artificial structures to confine the carriers for more longer time. So there have been many research on DRAM technologies. So the flash memory technology, PRAM and RM and DRAM technologies I have developed so far, I have researched so far are aiming to the industrial memories. So there are many numerous researchers in Korea and all over the world, but silicon compatible material based and very strong, very reliable memories are welcomed by the industry. So that is my first goal in doing my researches. So memory devices for neuromorphic system. Neuromorphic is a very famous terminology in these days. So semi-floating gate synaptic transistor. So synaptic transistor is a transistor that realizes the biological behaviors of synapse. So there can be many functions. We already know many functions of the synapse, but there can be unknown functions still. But as far as when it comes to known functions, we can pick up some representative functions like long-term, short-term potentiation memory, and long-term depression potentiation function. So, this synaptic transistor is closely related on memory technology. So there is no exception. There is no exception when it comes to synaptic transistor, although we can call this transistor because it is based on MOS technology. We can call it a transistor that has gate and source and drain and body, but there should be a memory storage. Can be a permanent carrier storage or temporary storage, like 1 DRAM, or it can be flash, or it can be RM. So every memory can be the fundamental ingredient structure for synaptic transistor. So I can say that the synaptic transistor cannot exist without the memory technology. So device schematics and operation principles can be explained in the first figures, and long-term to short-term to long-term transition can be found by simulation rules like that, transition time simulation, and the charge, the amount of charges in the floating gate charge and nitrile layer charge is depicted as a function of the transition time. So the semi-floating gate plays a role as the short-term memory storage. So after above a certain number of pulses, it can it becomes easier to push the temporally stored electrons or holes into the nitrile storage layer at a lower, smaller operation voltages. If we think about a NAND flash memory, the program or erase operation voltages reach 15 to 20 volts in magnitude, which is very large. But if the pulse operations is made much lower potentiation, or equivalent to program or erase operations can be realized at a much smaller voltage, like 5 volts or even 3 volts, as I remember. So in silicon germanium polymer charge trap synaptic transistor, and this is also evolved from the 1T DRAM with the silicon polymer structure. And if you look into the right side of the structure, you can see the silicon nitride layer for charge storage. So this synaptic transistor is a combination of polymer 1T DRAM and charge trap flash memory together. So after above a certain time, a certain number of pulses, the short-term memory is transit to long-term memory. And the rightmost figure shows the linear wave tunability depending on the number of pulses when it comes to the potentiation and depression at the same time in the same graph. So the figure shows a high degree of linearity and good symmetry about the point discriminating the potentiation and depression process. And partial dual gate is another synaptic transistor based on novel device structure. That is not a wire, but at the same time, what we can expect better from this device is the device fabrication and device structure is quite similar to that in the flash memory cell that is commercialized these days, right? So you may have heard of VNAND, vertical NAND. So the vertical NAND has the based on the cylindrical structure and the non-wire based flash memory cell. So if you drill the hole very deep, drill penetrating multi-layers, numerous multi-layers, metal gate and dielectric, metal gate, dielectric, penetrating all the layers simultaneously and in the reversed manner, you can deposit the dielectric materials like gate oxide, gate dielectric channel material, and I mean the ONO storage layer and tungsten oxide and channel material and oxide core, things like that. In the reverse manner, the materials can be stuffed into the narrowly drilled hole in the vertical array. So the materials, the only difference is the material combination. So if you replace the oxide core by a metal gate or highly doped polysilicon gate, we can call it core gate. And there is another rear gate at the shell, so we can call it core shell and dual gate. Okay, they can be operated independently. So they can be also welcomed by integrated device manufacturers, right? The final purpose is final destination we are aiming is always chip production, right? As electrical engineers, that is the main goal. So the below figure shows the evaluation of learning capability of the device and the device-based array, snap array. So the array level simulation or pattern recognition test can be performed by Python or MATLAB coding after extracting some primary device characteristic, device parameters of the designed or fabricated devices. And sideward dual gate snap transistor. This is also based on flash memory, and flash memory is very close to, as shortly mentioned, the flash memory charge to memory can be easily applied to transfer to synaptic transistor applications. So the the measurement result shows the signal level, which is equivalent to 4-bit operation, can be realized by ISTP operation. And if you apply identical pulses to modulate the weight, we can expect wider number of pulses. The pulse operation window but at the same time the weight range can be a little bit reduced. There is a trade-off relation between depending on how the snap transistor is operated by a set of prepared bias schemes. So the synaptic operations can be realized by non-volatile memories, but also can be realized by volatile memories. So if you think about the neuromorphic system is a kind of accelerator of some operations or helping the rear central processing unit. It doesn't really matter if the synaptic device is volatile or non-volatile. So, so you can think about the low-E chips manufactured by manufactured by Intel. The chips are based on SRAM, so the synaptic devices does not really have to be non-volatile always. So I have thought about some DRAM or SRAM based synaptic devices at the same time. So previously in the past research history, once I developed 2P1C DRAM cell, and I truncated capacitor, and I wanted to sustain 2 transistors only for DRAM devices with better reliability and operation ability. So this is the basic electrical characteristics, and the two important figures are drawn down there. And therefore, there are 2 modes. 2 modes can be expected depending on the amplitude of pulses. So better for DRAM operation, there is a mode better for DRAM operation, and the other is better for synaptic devices. For synaptic devices, it should be much better. We can expect modulatable weight changes, right? So, but if the pulse, even though we deal with volatile synaptic device, same thing can take place as we could observe in the non-volatile memories. So the thing is, we should be able to expect larger number of weights, and the weights can be modulated evenly with even spaces. I have better results than that, but it took some time to transfer the raw data to to origin graphing. So that is the best figure that I can show you at this moment. But the progress is very well going about 2 transistor synaptic transistor cells. And to terminal TRAM synaptic device, this was fabricated, and TRAM was also has been considered as the base structure for DRAM assembly. Actually, quite for a long time, quite a long time. So this was fabricated, and depending on the device footprint and depending on the operation voltages, we can expect a different level of conduction current. That is translated to the fact that there can be lots of weights when it is operated as a synaptic device. Okay. So next, neuromorphic, and then I would like to introduce a little bit about processing memory, and that can be called, or also called, memory search processor and MPU. That's a nickname I proved. So in artificial intelligence and semiconductor memory devices, I emphasize the relation between semiconductor memory device technologies and artificial intelligence. That there is a biological nervous system as nature, and that is translated to mathematical words and software words, and that has been driving the artificial intelligence technology so far. But we are living in neuromorphic system, neuromorphic engineering era for artificial intelligence. Neuromorphic means hardware side renovation for artificial intelligence. So for hardware, all circuit AI chip can exist, and I'm talking about more actively memory device involved neuromorphic systems. So the memory devices can be PRAM, RAM, anything SRAM, DRAM, and flash memory. Flash memory is one of my favorite memory devices, because we can expect a very narrowly and evenly spaced weight tunability. And neuromorphic versus processing memory. So there's a huge difference between a neuromorphic and processing memory. From the function point of view, the neuromorphic system is a subset to processing memory architecture. So there's a von Neumann architecture, non-von Neumann, and there's a neuromorphic down there. So neuromorphic doesn't have to be PM. PM does not have to be neuromorphic. So the subset and ordinate and subordinate relations are quite difficult to simply define. So if you look into this diagram was drawn by myself after reading many papers and recent articles. So this is quite this can be quite correct to some large degree. So it is the relation, the subset relation is quite a little bit complicated, but neuromorphic is surely different from PIM technology. But PIM we are, even though we have not named certain technology as PIM, but every computer architectures, every electronic devices, including logic devices and memory devices, have been developed toward the PIM architecture. And neuromorphic can be helped by the PIM technologies, and also at the same time, neuromorphic is subset to PIM technology when it comes to function, how various the functions can be expected. So international technological movements, the United States, China, and France, and what else? Japan are pursuing the PIM technology in recent days, and you also have heard of the HBM PIM or functional memory film announced by Samsung recently. So the ultimate form of PIM. So here's another rendezvous between device engineering, the memory device, and PIM. So the final destination is up to this point, the PIM largely implies that the near memory computing, the memory area and computing area, logic area, the distance between them has been shrunken at best with the best technologies that can realized in a certain generation. But the final destination is to move the memory array into logic device, or logic device logic array into the memory array. And the real final ultimate form of PIM is single cell integration. The computation capable memory device developments will be realized, and this is the goal of my research, and this is the future electronics which I can conclude with. So PM is the beginning and the final destination. So you can understand why PM can be final destination, but why is it can't be the beginning? So if you look into the papers related to PM technologies, the PM, the terminology of PM dates back to the history of the first invention of computers. The paper I first saw, the PM terminology was published in 1957, which was really a long time ago. So right after computer architecture was invented, people wanted to merge memory and so logic part together. So MPU, memory-centric unit technology will make the defense or test. What does that mean? We have been world first for the semiconductor industry and engineering of the world, and that will help us make the defense of past and that will help us live toward the future future electronics and semiconductor. Okay. So this is the final story of my talk today. Time a little bit past, but I'll try to shortly conclude. So the first master transistor and the first silicon non-volatile memory were invented by Korean researcher who worked in Bell Laboratories a long time ago. And they were invented in 1960 and 1967. So recently, you may have heard of semiconductors in broadcasting and newspapers, but I believe the silicon semiconductor technology has been ours from the beginning, right? Okay, so two major inventions, silicon MOSFET and silicon memory, are ours actually. So Korea is a blessed country for semiconductors. We have three seas facing everywhere, and that is blessed natural environment for semiconductor production. So among semiconductors from years, you have been taught how to precisely use chopsticks from times when you were very young. So we have minor preciseness cultivated from youth. That makes Korea strong with semiconductors. One interesting background story. And another thing, this is a famous Korean traditional phone screen, right? So this is the K diagram I first demonstrated at the beginning of the talk today. So I saw this figure EK diagram in 1998 when I was a third year undergraduate school student. So I was really fascinated by this figure, but I totally did not know about the meaning of this figure, how to draw it, how to interpret it. But whenever I see this figure, I was really excited and fascinated. So that's why I'm working as a researcher in a semiconductor area for Korea and for other people now. So I really thank again all the professors at SNU who taught me EK diagrams and semiconductor engineering at this moment again. So we have people, Korean people recently cooperation in incessant achievements. So we are very rich with memory. We have very many things to memorize, and we need memory, technically memory for future electronics. Okay. So entire galaxy in Cas necklace marble. This picture was taken from a very famous film, Men in Black, MIB, and Gallus, the agents wanted to kill from aliens was preserved in a very small marble in the necklace of cat, right? That reminds me of the EK diagram. EK diagram is all the electronic structure phenomena that can be taking place in the solid state, and that is folded to a single space, very small, tiny space, Will and John, and that shows a very good analogy. So that was a very famous scene from the movie. So last but not least, I would like to say is with this figure is the electronic technologies and future electronics and the contributions to the world and society can be skimmed in this place where you are. So by what theory? By blow theory. Okay. So I encourage everyone here today. I thank all. I give my sincere thanks to all the audience today, and I would like to talk about more about the future electronics and memory device technologies sometime in the near future together again. Thank you.
네, 발표 준비해 주셔서 조성재 교수님께 감사드리고요. 혹시 시간이 좀 지나서 그러는데 혹시 질문 있으면 짧게 하나만 받도록 하겠습니다. 네, 별다른 질문 없으시면 혹시 질문 있으시면 개인적으로 조성재 교수님께 메일 보내셔도
예, 여기 마지막 페이지에 이메일 주소 있으니까요. 네, 궁금한 거 있으신 분들은 언제든 편하게 연락 주십시오.
네, 그러면 조성재 교수님께 다시 한번 감사드리겠습니다.
예, 감사합니다.
네.